Hello everyone. Today we are here with a PPT of innovative examination for COM, computer organization and microprocessor. So in this PPT we are gonna solve few questions of gates in of the year 2019. Our group members are me, Sarvesh Yadav 61, 62 Vaibhav Yadav and 63 Aman Yogi. So we will begin with the first question. Over to you, Aman.
Thank you, Sarvesh. Now we are moving on to the first question of the GATE examination of year 2019. So the question is, a certain processor uses a fully associative cache of size 16 kilobytes. The cache block size is 16 bytes. Assume that the main memory is byte addressable and uses a 32-bit address. How many bits are required for the tag and the index fields respectively in the addresses generated by the processor? So let's look at the question here. We'll see what is given in the question. The cache size is 16 kilobytes. The physical address is like 32 bytes, and cache block size is 16 bytes. So in this question, they have asked us to find the number of bits in tag field, number of bits in index field. So in fully associative mapping, the physical address is given by tag plus block offset, the summation of tag and block offset. So here we have the physical address and the block offset. So we can find tag value easily. So it turns out to be 28 bit. In fully associative mapping, index fields is included in tag field. There is no separate field for index in fully associative mapping. Hence number of bit in index field is 0. And moving on to the next question, which is question number 2. This was also asked in the GATE examination of 2019. A certain processor deploys a single level cache. The cache block size is 8 words and the word size is 4 bytes. The memory system uses a 60 MHz clock. To service a cache miss, the memory controller takes one cycle to accept the starting address. Then it takes 3 cycles to fetch all the 8 words and finally transmits the word of the requested block at the rate of 1 word per cycle. The maximum bandwidth for the memory system when the program running on the processor issues a series of read operation is dash bytes. So the approach to this question is given by, we have the formula for bandwidth, which is bytes transferred per cycle time. So the bytes we have is 32 and the time taken totally is the 1 second for the cycle to accept address and 3 cycles to fetch the 8 words. So therefore 1 plus 3 plus total we have 8 words per word 1 cycle. So 8 into 1, that is the overall time is given by 12, and hence we can calculate the bandwidth with both of these informations, and hence the bandwidth turns out to be 160. Now I'll hand over the PPT to Vaibhav Yadav.
Moving on to the next question. So the question is the chip select logic for a certain DRAM chip in a memory system design is shown below. Assume that the memory system has 16 address lines denoted by A15 to A0. What is the range of address in hexadecimal of the memory system that can get enabled by the chip select CS signal? So we have got the memory system which has 16 address lines, which is represented by A15, 14, 13, 12, 11, 10, which will go up to A0. So according to the question, A15 equals to 1, A14 equals to 1, 13 equals to 0, A12 equals to 0, A11 equals to 1. So the possible range in binary would be in the first address 1 1 0 0 1 0 0 0, which will go up to A0. So the final first address would be C800. Then coming to the last address, last address whose possible range in binary would be 11001 111, which will go up to A0. So the final last address would be CFFF. So the possible range of address would be C800 to CFF. So the final answer in the question is option A, C800 to CFF. Thank you. That was by my side. Handling over to Sarvesh.
Thank you, Weber. So this is one of the most easiest question of GATE 2019. The question says that in 16 bits second complement representation, the decimal number minus 28 is. So first we have to convert the 28 into decimal form, which is triple 100. Then we have to convert it into 16 bits. So the 16 bit will be 4 times 0, 4 times 0, triple 0, 1, double 1, 0. So then we have to convert the minus 28 into its 2's complement. So the 2's complement for this will be 4 times 1, 4 times 1, triple 1, 0, 0, 1, double 0. Thank you for listening us. Signing off.